Okay, thank you so much for joining me today while I discuss energy, conservation of energy, and touch on work a little bit. So the first question we can ask is, how do we define energy? Energy is actually a little bit of a challenging concept to define, but it is essentially a scalar quantity. So scalar meaning it doesn't have any direction like velocity or momentum does, but it's a scalar quantity that we associate with a system of one or more objects, and it helps us describe the system. Energy is measured in joules. So a joule is a kilogram times meter squared over second squared, or we can also express it as a Newton meter, right? Newton we learned from studying force. Now, energy cannot be created or destroyed, and it's useful to think of energy kind of like money. Money in the bank that you already have, not money that can be printed and destroyed. Think of it as money that is inside of your bank account that can be transferred or converted to different currencies. There are two types of mechanical energy. So we have kinetic energy, which is expressed with a K, and that comes from whenever an object has a velocity. So consider like a ball rolling down a hill or a pendulum swinging. We can have a velocity in these scenarios. And so kinetic energy is expressed as 1/2 mv squared. So it depends on the mass of the object and the velocity of the object. The second form is in potential energy, which we typically express with a U, and it can have a couple of different forms, such as gravitational or spring. Now, gravitational potential energy, denoted U sub g, can be expressed with mgh. So it depends on the mass of the object, the acceleration, the rate of acceleration due to gravity, and the height of the object. And then for a spring, U sub s, we express it as 1/2 kx squared, where k is a property of the spring. So it depends, it's called the spring constant, and it's a property of the spring. And that is multiplied by x squared, where x is the distance that you've either pulled the spring or compressed it, right? There's always that equilibrium part where if you leave a spring alone, it'll sit at that distance, that length, and then how far you stretch the spring or compress it. That's going to be x. So energy can be transferred, and that's how we get work. So work is either the change in kinetic energy, or it can be the negative, the change in potential energy. Now, energy must be conserved, and that means that the initial energy must be equal to the final energy. Energy can't just disappear or be created. And we can take a look at what that, how that manifests here. So consider a pendulum at rest. So we can take the bottom where the pendulum is hanging at its lowest point. We can take that as a height is equal to 0. Let's mark that as our 0 height. Height is kind of a little bit arbitrary. We can set it to wherever we want. For a pendulum example, it's most convenient to call it h is equal to 0 at the bottom. So in this scenario, we have no motion, which means we have no kinetic energy, because remember, kinetic energy is 1/2 mv squared, but v in this case is 0. So the kinetic energy is 0. And since we've taken the bottom position as height is equal to 0, that means there's no potential energy, because potential energy is mgh, but h is 0. So potential energy is 0. That means in this initial state, let's call it state 0, that means that the total energy is equal to 0, since it doesn't have any kinetic or potential energy. Now, imagine holding the pendulum at some height, let's call that h1, and that's above the resting point at the center, which is h0. While we're holding it there and preparing to drop it or preparing to release it, so let's call this state 1, it's still not moving. So K sub 1, which is the kinetic energy in this state, in this condition, is 0 joules, because we're holding on to it. We haven't released it quite yet. And then the height is not 0, because now we're at some height above h is equal to 0. It could be, say, like 3 centimeters, something like this. And so now our potential energy is not 0. So in this state, in state 1, all of the energy is potential energy. So E1 is equal to UG1, which is equal to MGH1, so non-zero. Now, let's consider a second state, state 2, where we've released the ball. You know, the ball is release the pendulum. So the pendulum is now swinging downward. And at take a snapshot before it hits h is equal to 0. And now it's at some height h2, which is still above h0, but also below h1. So if h1 was 3 centimeters, then maybe let's say that h2 is 1.5 centimeters, something like that. Now the ball is swinging, and it's at some height above 0. So it has both a kinetic energy and a potential energy. The kinetic energy is 1/2 mv2 squared. Let's say its velocity is v2 in this case. And its height, so it has a potential gravitational potential energy, mgh2. And so the energy in this case is both kinetic and potential. So what we've seen happening between states 1 and states 2, states 1 and 2, what we're seeing is a transfer of energy. It was all potential energy up here. And now it's got some blend of kinetic and potential energy. But it's important to know that the energy in state 1 is equal to the energy in state 2 because energy must be conserved. So that means the potential energy in state 1 must be equal to the addition of, is that a 2 there? So the sum of both the kinetic energy and the gravitational potential energy in state 2. So if we knew some of these values, we could solve for maybe an unknown. All right. And then consider a case like this, where at the bottom, the pendulum will continue to swing, but its height now, what we'll call h3, is actually back at what we called h0 originally. So its potential gravitational potential energy is going to be 0 because it's back at the 0 state, what we called a 0 height. But its kinetic energy, unlike state 0, where it was just kind of sitting at the bottom, now we have released it and it's going to have a velocity. Let's call it v3. And so the kinetic energy at this point is expressed as 1/2 mv3 squared, which does not equal 0. So what we see in state 3 is that the energy is, has no gravitational potential energy, and it's all in the form of kinetic energy. So the energy at E3 is equal to 1/2 V3 squared. And remember that the energy, it must be equal in all of these states. So that means that the potential energy here must be equal to the sum of the potential and kinetic energy here, which must be equal to the kinetic energy here. And we can use this to solve for maybe some unknowns in the system based on what information we have. Thank you so much for listening to my little mini lecture about energy and conservation of energy. And we'll discuss further next class.